about how coated rebars somehow weren't fulfilling the purpose that they were set out to. And essentially, the point of failure lied in the fact that these discontinuities or pinholes or damage that the coating underwent during storage, transportation, and construction ultimately led to the downfall of this technology. I've also put up here some excerpts from a report that were published by 3 agencies, the Canadian Strategic Highway Program, the FHWA, and the Florida Department of Transport, which basically talks about why coatings should not be used as a primary protective system, especially on highway structures, because of the number of failures or collapses that have been documented over the years.
Can you please conclude in a couple of minutes?
Sir, I've just started 2 minutes ago.
But see, okay.
I've not even, sir, that's...
Yeah, you are allotted 10 minutes. I think you have consumed most of it. Anyway, please
not,
go ahead.
Sir, I'm keeping track. Don't worry about it. All right. So coming to what is being increasingly noticed as a trend across India as well as the globe is the use of what are known as corrosion-inhibiting admixtures. Now, these are essentially liquid admixtures that are admixed right to the concrete, which is a chemical that in fact reacts with the surface of the steel and forms a chemical protective barrier alongside the entire external surface of the steel, preventing the steel from corroding or interacting with the external environment of chlorides, oxygen, moisture, and so on. So just to show you a visual demonstration, this is a rebar. The right-hand side is placed in water with the corrosion-inhibiting admixture, the left-hand side without, and this is the sort of protection that it affords. The same sort of experiment conducted with concrete as well as rebar in concrete as well as a post-tension cable. So the left-hand side is without the control and the right-hand side is with. So this is just to give you a visual idea of how these systems work. And a little bit about the mechanism. So what you see in these yellow particles moving towards the steel are in fact the chemicals. So these chemicals are what are known as ligands or chelating materials. So chelating materials are materials that have a very strong affinity to metals. Similar chemicals are also used in medical science. So when the human body undergoes heavy metal poisoning, such as poisoning with mercury or lead, we're injected with certain chemicals or medicinal chemicals that have a very strong affinity to these metals and, in fact, go and find the metals within our bloodstream and flush them out. The same technology, the same mechanism, however, applied to steel. So these chemicals have that same very strong attraction to steel and have no choice but to go and bond with the surface of steel and form a barrier layer around it, overcoming all of the shortcomings of a typical coating system. So the possibility of a pinhole or a break in this kind of a coating becomes almost nil because it's a chemical reaction that actually takes place at the surface. The mechanism can be read in detail in the paper, so I'll skip that and move on to the case study. Also, another important factor is that this layer can actually be measured using electrical impedance spectroscopy. So it has been physically verified to provide protection as well. This slide here is a collection of papers published by NACE, so that's National Association of Corrosion Engineers, that date back to the early 70s. The idea behind putting this on this slide was to show, or rather to talk about how this technology has been around, has been used, has been published since the early 70s and 80s, as far as being a reputed and a proven corrosion protection technology. Next up are some case studies from the Strategic Highway Research Program, which publishes results on the basis of ASTM G109, which is the test used for predicting the behavior of corrosion protection systems in concrete. A few conclusions of this study were that use of such admixtures result in a 17-year delay in the initiation of corrosion. Average half-cell potentials are less by 22%. In terms, as compared to the control, so as compared to elements that don't have corrosion-inhibiting admixture systems used in them. And the treated sides have corrosion currents which are about 40% lower than the control. This table here is a Life 365 analysis of the cost as well as life, so the cost benefit, so to speak. I want you to look at the highlighted portion which talks about a coated rebar versus a rebar that is protected using a corrosion-inhibiting admixture. So you see roughly a double increase in initiation time as far as corrosion is concerned. And in terms of time to repair, we see about 30 years with a epoxy-coated rebar, whereas a corrosion-inhibiting admixture system goes up to 45 years. Also, the IRC has studied this system quite extensively and has sort of been very encouraging as far as accrediting it for use in India as well. So various state PWDs, metro rails, railway bridges have started using this system as well. So to give you a few examples, these are the bodies that are already successfully using it commercially. A lot of these bridges are being instrumented. So we are publishing results for the reduced corrosion potentials as well as the reduced half cell potentials of treated segments and treated areas. The railways have made extensive progress on this technology. They've actually published what is called a technical literature on corrosion and carbonation protection called the BS88, which actually outlines a complete standard for the use of corrosion-inhibiting admixtures. So this is something that, that all of us can use as well. There's a specification number here at the top of this slide, which is an RDSO specification. ASTM G109 results for corrosion.
Can you please wind up, because we have to go through some formalities also before closing this session.
Sir, I have one more case study for a structural steel bridge.
I think you'll have to skip. We'll have to skip, because other things, we have to close the session. We have to have replies. Some few replies are there to be given to the questions already with us.
Okay.
So you'll have to skip that. And you can ask for, presentation. You are given only 10 minutes. I think you have crossed 10 minutes very much more than 10 minutes you have gone now. So, you see, the problem is of time. I don't have time with me. I was given very little time. We had to manage within that time. So, very sorry about that. But you can have maybe discussions with other people if they are interested in that. The paper is already published, isn't it?
Yes.
You can just refer to it and then close as quickly as possible. Thank you.
Sure. So can I conclude or?
Yes, please conclude.
All right. Okay, so I just want to, before concluding, I'll talk about one more slide for the structural steel bridge and then I'll conclude. Okay. So the second case study that I was going to present was for a structural steel bridge. So this is also a structural steel bridge constructed in Goa over the Mahade River, which is a saltwater river. This bridge was in fact 1 year old and was already showing signs of advanced corrosion. So the treatment scheme that was suggested was one that was been used for the first time in India, which is, it was decided to provide a galvanic corrosion protection system in addition to typical epoxy PU coating systems that are used on structural steel bridges. So when I talk about a galvanic structural steel protection system, what I mean is the installation of sacrificial anodes. So sacrificial anodes, as most of you know, are metallic anodes that are made of metals that are more corrosive than steel, which are combined with the steel or put in electrical connection with the steel, so that under attack from corrosion-causing factors, these sacrificial anodes corrode, they sacrifice themselves and protect the steel that they're connected with. So this table here on the right-hand side gives you the reactivity series of metals, where steel is right here in the middle. On the bottom are the more the noble metals, or metals that don't corrode, extremely stable metals, and right on top are the extremely reactive or very, very corrosive metals. So the idea is, if you are able to combine metals that are more reactive than steel in the same electrical system as the steel, during an attack from corrosive substances, these more reactive metals sacrifice themselves and protect the steel. So this was done for this bridge in Usgaon. So these little installations that you see are the anodes. And then a usual scheme of an epoxy primer and a polyurethane top coat to protect it from corrosion. And the interesting part about this is that this entire bridge has been instrumented and is being checked since 2011. So the thickness, the conclusions have the results from the inspections. So the thickness of the truss was measured at about 243 locations across the bridge, and there was found to be no change in the thickness. So that means no physical corrosion seen from March 2011 to September 2016. Corrosion potential readings were taken at about 339 locations. And it was seen that about 81% of the readings showed that there was no corrosion. The coating was also checked at all 339 locations for cathodic disbondment, and no cathodic disbondment was also observed at any location. So in conclusion, I talked about two systems, one for RCC bridges, by way of bipolar corrosion inhibiting admixtures, which try to overcome some of the known issues related with coatings. And number two, we talked about structural steel bridges and the use of galvanic corrosion protection systems in addition to using typical coating methods. Thank you very much, and I'll be happy to take questions, or if you wanted to discuss this in detail later on because of the paucity of time, I'll be available outside. Thank you very much.
Thank you. I think we've got just a few minutes. Professor Tandon has agreed. He has got 4 questions. He will give very short answers for these questions. And if you need some further information, you can discuss with him during lunchtime. Also, Mr. Harsimran Singh also has 1 question. And we have to close immediately, so in a very short time, they'll give you whatever possible, whatever replies are possible.
First question is from Mr. B.K. Sinha, Chief Engineer, MORTH. Why an arch bridge was not possible to construct at the location, as ends seem to be having strong, hard rock. Basically, the arch bridge was a good solution and is always will remain a good solution. It would become about a 175 meter span instead of 114 meters which we had here. So I would say that economy was the only reason why we didn't go for it. So it's, of course it would look perhaps as beautiful or more beautiful than whatever you see in this 114 meter span, but economy was the main issue. Second question, cartilage were required during construction or during service also? Both during construction as well as during service. During construction you have a problem that there can be an overturning of the whole structure. You've got only 30 meters to stabilize a span which is about 60 meters in the, on the other side. So you can have a problem. In service conditions, you again require that because you are getting a uplift at the end bearings. So in order to be able to stabilize the structure and not start getting tensions at the bearings, which nobody wants to, no engineer wants bearings to go into tension. So then you have to go stabilize. Its use is also during service. Okay.
I have been told by the organizers that we need to close immediately. So we are, the remaining questions, the people who have given the questions can please meet Mr. Professor Tandon or Mr. Harsimran Singh during lunchtime and get clarifications. And just before closing, I must give 1 minute to my co-chairman.
Thank you very much. I'll conclude in 1 minute. This technical session had 6 papers with so enthusiastic presentations. So enthusiastic that made our respected chairman a bit trouble. But those papers are all very excellent level internationally. And I'd like to congratulate all presentators on their very, very fine work. Thank you.
Thank you. Sorry for keeping you from lunch. And I'm hereby closing the session.
Thank you very much, sir. May I request Madhvi, Ranjita, Shirisha, Saundarya and Meena to kindly give the mementos to the authors of, who are in the dais. To Professor Mahesh Tandon, Mr. Harsimran Singh ji and Ishita. And on behalf of Indian Road Congress, I would like to thank the session chair, Mr. Nenan Koshi, and our co-session chair from Japan, Mr. Daichuki. And I request Madhvi and Ranjita to present the memento to both of them. Thank you, sir. It was really difficult with so many papers, and you conducted it quite well in time. And now we break for lunch, and after lunch we assemble again for the next session here.